Welcome to lecture 22. This should be our last lecture for chapter 7. We're going to talk about, now that you've been introduced to elimination reactions, and we're going to talk about the E1, E2 comparison, and then we're going to incorporate, if we have SN1, SN2, and kind of the deciding factors. So that's one thing I want to talk about in this lecture session. The other thing I want to discuss is Zatzes. So you can see it written that way. Zatzes versus Hoffman product. Okay. And we're going to talk about what this is. And it's all determined by the bases. And you're going to find that these are determined by the bases as well. Okay, so this is going to be a lot of what the bases tell us. And you're going to have to kind of memorize some bases and categorize them. And then I want to talk about alkene synthesis by dehydration of alcohols. And this is always going to be an E1 mechanism. And you've already talked about the E1 mechanism, so that'll be good. And then I'm going to wrap up with the E2 mechanism because it's stereospecific. So you're going to have to pay attention to this when you have certain conformations. So you're going to see some Newman projections. And you're going to see the chair conformation. And so I'm going to try to teach you how to predict the correct product. And Sapling has some excellent problems on this. This will be PG10B. Okay, so first let's talk about E1 versus E2, now that we understand what those are. Okay, so it's about the base. So if you have a weak base, that's going to be an E1. And a weak base has to be an ionizing base, okay? This needs to be ionizing. What does that mean? That means it's got to stabilize the carbocation. That means you want some protons, okay? Water. These are polar protic solvents. A lot of times your solvent is your base. E2. E2 is going to be strong base. And so a strong base would be, I think, of a negative charge. So like sodium hydroxide is a very strong base. That is an OH minus. Sodium alkoxide, something like this. This is essentially the methoxide there. So these require strong bases. The solvent, these solvents are going to be polar, just like, but these are going to be aprotic. Okay, we don't want that proton around because it'll shut down our negative charge. Okay, we do not want it shutting down our negative charge. Here we want the proton around to stabilize that carbocation. So, and the effect of the substrate is going to be the same. So here you're going to see the tertiary rate of reaction will be faster than secondary, faster than primary. In fact, primary usually will not go E1. Because you're going to have to compete with substitution. Okay, SN2 is going to happen on something like that, or E2. Kinetics, you should know your rate laws by now. At E1, you have the rate is proportional to the alkyl halide. Over for E2, the rate is proportional to your substrate and your base. Orientation, you're going to see that E1 is going to to be SOTSAs. So you're always going to get the more substituted alkene. So when you label the beta carbons, you need to take the hydrogen away that will give you the more substituted, the more stable alkene. E2 is usually SOTSAs. Okay, so it usually goes SOTSAs. There's going to be some conditions when it doesn't, and you will see that. Um, and that's what we're going to talk about in PG10B. Also, there's a Hoffman base. Okay, so what are your Hoffman bases? There's like 4 of them, and I am going to see what page they're on. Hoffman bases. I think I'm going the wrong way in your book. Let's see. Hold on for just a second. Okay, Hoffman product. The least substituted alkene product is page 364. So let's turn to page 364. Yes. So page 364, your Hoffman bases include tert butoxide. So a lot of times you'll see it like that. Okay, that's a strong base. You'll see diisopropylamine. Okay, diisopropylamine. This is tert butoxide. Triethylamine. Looks like that. You might see it like this. And 2,6-dimethylpyridine. All right, so what do these have in common? They're bulky bases, people. And that means they're going to take away the hydrogen. They're going to eliminate the hydrogen that's the least crowded. And so this is going to be, it's going to give you the least substituted product. So this is the opposite. This is the Hoffman, and these are Hoffman bases. And so then it'll take the beta hydrogen that has the most and to give you the least substituted product anytime you have those bases. And you can see those results on page 365. Okay, so that is kind of touching on that. The other thing I wanted to talk about is the competition between substitution and elimination. My key when I want to do an elimination, I'm going to add heat. Okay, so I'm going to add heat. Unless you have a strong base and you have a tertiary substrate, folks, that can only go E2. Okay, so what does that look like? That looks like something like this. So there's some reactions that can only go a specific way. So you have this and you have sodium methoxide. You can see that like that, or you might see it like this. Okay, same thing. Now, this is a tertiary alkyl halide. And you can be like, oh, okay, tertiary alkyl halides, they like to go SN1, and they like to go E1 and E2. All right, I know I'm going to form my carbocation. All right, that's not true. This is a strong base. Okay, this is not compatible. You have to have weak bases. You would have to have methanol to stabilize this carbocation. So these are not going to be in the same solution together. So what's going to happen is you got your alpha carbon, you got your beta hydrogen, and what's going to happen is this strong base is going to eliminate. Okay, and that is an E2 product. You're never going to get that carbocation. You got an E2 elimination, and because you have a strong base. A compound example of a reaction that will only go E1. Okay, so you got something like this. OH, horrible leaving group. Okay, it's not going to leave. In fact, if you want to make it into a good leaving group, this is one that you have to use a base, pyridine. Sometimes you'll see it like this. This is pyridine. You use a base, and you add tolusyl chloride. This is tolusyl chloride. So sometimes you'll see tolusyl chloride, something like that, or TSCl. And so what happens here is your OH here goes, and this leaves. It's kind of like an SN2. I'm going to say like SN2. And that's how you make the tosylate. And you don't have to draw this all out like this. You've probably seen it like this. Excuse me. This is one of the world's best leaving groups. Excuse me. Okay. World's best leaving group. So something like that's going to just leave, and then you can get your carbocation here. Okay, so that's one way to turn a horrible leaving group into a best leaving group. Another way is to add acid, and the acid you usually use is sulfuric acid. And what that does is that protonates the OH. So now you have an acid-base reaction, right? And you've protonated this. This is water, another one of the world's best leaving groups. So, that's my carbon there. So this is going to leave, and now you have a carbocation. And so, in that case, this HSO4 minus is not a nucleophile. Okay, not ever going to be a nucleophile. So that means you've got elimination. HSO4 then can take this hydrogen here, which is beta, and now you have an alkene. Okay, this is an E1 because you are forming a carbocation. Sulfuric acid has ionizing solvent compatibility. A lot of times you'll have water in here. Water has hydrogens that will stabilize that carbocation. So that's an example of an E1. This is an example of an E2. Other than that, a lot of times it's just going to be a secondary alkyl halide, and if you have a strong base, then it's going to be an elimination product. Compounds like okay, so here's a secondary, and you have sodium iodide. Okay, iodide is a nucleophile. Iodide is never going to go and get a hydrogen. Why? Because this is a strong acid. Also, Br minus, okay, it's never going to do elimination. HBr, no, these HI and HBr are 100% dissociated, right? Because they're strong acids. So those are not going to be bases. So anytime you get an ion, like sodium iodide, then you can say, okay, secondary, that can do an SN2. And if this was coming at you, then this would be coming back, and that mechanism would be SN2. So those kind of things. you should be able to see if you had something like this and you have sodium methoxide, then you're going to say, okay, well, this is going to be a base. What if you have heat? Then here's your alpha carbon, and you're going to choose the beta hydrogen that's going to give you the more substituted alkene, and this would be E2 because you have a negative charged strong base. So that is how you determine those questions. What is our other goals? I think that's pretty much our other goals. So we're going to go on now to the POGL. Okay, so looking at POGL 10B, oh boy, I get to draw this stereochemistry. You know why I don't just bring these in? Because that might not be good. Copyright issues, okay? So we're going to do the stereochemistry of the E2 elimination. Okay, so we have, what's that sentence say? It says it has to be 180 degrees elimination and tie, 180 degrees apart. This is compound A, and these three lines means it's the same. Now I'm going to draw a Newman projection. I'm drawing that Newman projection so you can see that. That's how we determine the dihedral angle. pH equals phenyl, and that's C6H5, and that is what a phenyl group looks like. Okay, now we have to rotate this so that the Br and the hydrogen are anti. Okay, you see how they're circled here? We can even do them in different colors. So here's your Br and this is your H. Here's your Br and here's your H. Okay, and you know those have to eliminate. But right now, they're not 180, are they? What's the bond, the dihedral angle there is 60. Okay, so that's not going to happen. So we're going to rotate, and we're going to rotate this back carbon. So it looks like I draw this front carbon the same. Whenever you're working with Newman projections, it's best to only rotate one. So if we rotate that back carbon, and now we put the hydrogen up on top, and then that puts the CH2, CH3 on the right, puts the other CH3 on the left. This is compound C, and now they're showing you how to draw this into the wedge. Okay, so here you have H on top, and now we have these as 180. Okay, and then what does this do? So everything on this side here is on the same side, and everything on this side is on the same side. So when I've drawn this, you see how we've decided the phenyl on this front carbon is on the wedge. So there's the phenyl. That means the CH3 is also on the wedge. See? CH3 is also on the wedge. That means the hydrogen here is going back. This means that CH2, CH3 has to go back. This is going to be important. So everything on the same side. So if this is chosen to be your wedge coming at you, this is your dash. Because this is going to determine whether you have cis or trans. Okay, so now if you, this is the 180. So your dihedral angle now is 180 between the hydrogen and bromine. So if we lose the HBr, then what does this look like? See how the phenyl and the hydrogen on that first carbon, and then on the back carbon, we've got CH3, CH2, CH3. So if you convert that, then you have phenyl, CH3 on the same side. Here you have CH2, CH3, and hydrogen on the same side. Okay, so that's E. We'll see if we can answer our questions. For the reaction shown in Model 1 in structure A, label the alpha and beta carbons. So this is your alpha, and this is your beta. Don't worry about the phenyl, because that's technically not a beta because those are sp2. These are, see that? It's an sp2 carbon. When converting the wedge dash structure A to a Newman projection, compound B, which carbon is in front? Should you say the alpha? Confirm that A and B are the same conformation. To convert B to C, groups on the, which one? The beta. The beta. The beta were rotated. Okay. Confirm that C and D are the same conformation. Oh, I feel like we did that while we were drawing these. Okay, elimination of beta hydrogen, this is the blue hydrogen, only occurs when the hydrogen and bromine are anti-180 degrees apart. In which Newman projection is H and B anti? That's C. Okay, so circle C. In structure C, the phenyl and the CH, the phenyl and the CH3 groups are on the same side. You see, you got your phenyl here and your CH3 group. In the product compound E, the phenyl and CH3 groups are on the same side. So you see how they're all on the same side? Confirm that Newman E and the alkene are the same compound. The three possible staggered conformations of S2-bromobutane are shown below. Cross out the one conformation that cannot undergo E2 elimination from conformations shown with no further rotation. Okay, so you're not getting to rotate these, you're just going to look at these and see if they can work. Okay, so we have back carbon here, CH3, CH3, and then the front carbon, CH, and then let's figure out what that would be like. What would that product be? Okay, so you can take this hydrogen and that bromine, they're 180 degrees anti. Okay, so we can eliminate those, HBr. And if you do that, you have H, CH3, and then your back carbon, you have CH3, CH3. So then we keep these on the same side. And that would be that product there. Okay. Cross out the one conformation that cannot undergo E2. Okay, so let's look at the second one. So that one's good. We just did the product. And you're not able to rotate this. Okay, so there's your Br that's going to leave. The back carbon here, we have H, and then we have H here, and we have CH3 here. Okay, so these are 180. So if we lost the HBr, then the two that are on the same side are H double bond CH3, and then the two that are on the same side which are CH3 and hydrogen. So that would be that product. Okay, and then the last one. The last one has CH3 on the back, hydrogen here, hydrogen there. On the front, CH3Br. Okay, you can't take it from here. Okay, you can't do that. It has to be right here at the top. So put an X through that one. That conformation cannot undergo E2. There's no E2. Circle the one of the remaining two conformations that's most stable or of lower potential energy. Okay, so let's look at these. So out of the two, one of the, okay, so let's see. So out of these two, let me box them in. We're looking at either this one or this one. Which one's the lowest energy? So here we have, let's count how many Gauss reactions we have. So we have Gauss, and that's the only Gauss. So we have one Gauss interaction, and here we have 1, 2, 3 Gauss. So I would say that this one's your lowest energy, the one in the middle, because it only has one Gauss. Okay, I don't think I even did that one wrong. I think this is an H. So that would be 2 Gausses when I look back on it. Okay, C. From the two conformations that can undergo E2 elimination, use curved arrows to show the flow of electrons during the E2 elimination and draw the products. So I just did that here, okay? I didn't show you the flow, so you can just go back through there and you can show this. So your base comes in, takes that hydrogen, and those electrons go to that front carbon, and then those electrons go to bromine. And then you can draw this and then that product here. And on the second one, the base is going to come in. So you have one electron flow arrow to take the hydrogen, a second one pushing towards the carbon, and then a third one for the bromine to leave. So you need 3 electron flow arrows to show this mechanism. And there you have your product there. Determine whether the two alkene products are E or Z. Remember E? E is trans, and Z is cis. This is supposed to be a hydrogen, so that, do you see how when you look at this, you're comparing these two here between a carbon and a hydrogen. Carbon's on the same side. And then you compare these two, carbon and a hydrogen, the carbon's on the same side. So since both are priorities on the same side, this would be what? Z for cis. Okay, you look at the next one. And I think it was supposed to be H. Let's see what it was. Okay. Kind of got messy, hasn't it? This is H. Okay, so this is H. This is CH3. All right. So you see how between hydrogen and CH3 is your higher priority, and then between CH3 and hydrogen, CH3 is your higher priority, and those are both on the opposite, so that would be E, and that would be trans. Okay, D, determine whether the two are they the same or are they isomers. These would be cis and trans isomers, and they're actually called diastereomers. Predict which alkene would be the major product. Well, the major product would be the one that gives you the one gauche, because you're going to have this conformation. It's lower energy, so it's going to happen more. And then this leads to the trans product. So the trans is more stable, and it leads to the trans because the gauche, one gauche, lower energy conformation. Okay, 3A, draw a wedge-Newman projection viewed along the C3 and C4 bond of 3-bromohexane. Okay, so doing 3A, we need to draw a Newman projection of 3-bromohexane. So what I like to do is first draw hexane. 1, 2, 3, 4, 5, 6. On the third carbon, we need to put a bromo. Now I just put a wedge out there. It's the first thing I do. And then I count my priorities and see if this is S. If it's not S, then I'm going to switch it to a dash and a wedge. So we can put a dash here. Now we count priorities. We have bromine is 1. Then we got carbon, carbon. We got to go to the next carbon, 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 and that's a dead end. So this is number 2. And then this would be number 3. And if I connect 1, 2, 3, that is what? Counterclockwise. So that's S. And S stays S because hydrogen is in back. So that is my compound. I'm going to redraw it just to make it neat. I'm going to do the hydrogen back. And then it says draw a Newman along the 3-4 bond. Okay, so my eyes are looking here along the 3, and then the 4 is going to be my back carbon, and I can go ahead and do dashes and wedges for the hydrogen. So first one is going to be, I'm going to put so let me just tell you something else. See this zigzag? The zigzag you want to always keep in the plane. That's what I do. So on the zigzag, you have this group here. This is going to be a CH3, CH2. So this is CH3, CH2. And then the bromine is on the wedge. So I'm going to put the wedge over here. And then we have hydrogen over here. And then our back carbon, we have this group here, CH2, CH3, because it's on the zigzag, so it's in the same plane. And then this hydrogen coming at you is a wedge, just like the bromine. And then the other hydrogen is going back. Okay, so that's my Newman projection. Now, this is going to be less stable because we have gauche right here between our largest groups. So it says rotate, I'm turning the page for V, rotate the Newman projections of the bromine, so the bromine and the beta hydrogen, so one of these beta hydrogens, I'm not sure which one, at C3 and C4 are anti. There are two conformations where bromine and hydrogen are anti. Draw both conformations, determine which one's the most stable. Okay, so the reality is, so these are already anti, and we do have one gauche. So then if we want to rotate this, and we can do the minus the HBr, you can have your base come in here, take this hydrogen, we need 3 electron flow arrows, and then you've got this CH2, CH3 like that, and then on this ring here you've got CH2, CH3, and a hydrogen. So what does that look like? Okay, so that's trans. And then if we rotate this, where this hydrogen goes here, if we rotate, then we can keep the bromine there, because I remember I only rotate one. CH2, CH3. Okay, we're going to rotate this back carbon, and now we're going to rotate so this hydrogen is anti. That puts the red hydrogen up here, and the CH2, CH3 there. Now the base can come in, take this hydrogen and the bromine leave. Now you got H, CH2, CH3. There's your yellow. And you got the back carbon, where this is a hydrogen here. This is a CH2, CH3. And then if you were to do that, that would be H, H, and okay, so that would be that product. Okay, and once you look at the stability, this is even worse. Do you see how you have this group here with this group? Okay, that's big steric groups. There's gauche. And then you have another gauche here. Two gauche there. Okay, so the first one would give you the more stable product. And what's the name? It would be 3E hexene, because it's trans. Now, you're not always going to have to go through this exercise. Most of it's just going to be sapling, okay? So I'm not going to ask you to do a whole lot of this on the assessments, but I think it's a good exercise for you to understand that they're stereospecific. Now you will have to see Model 2. You will get a lot of kind of questions on Model 2 on my assessments. So put a star by Model 2 and let's work it. Okay, Model 2 is elimination in cyclic compounds. And so here we have the chair. And we have bromine here, hydrogen there. So we got axial, equatorial, axial, equatorial, and then we have this carbon here, axial, equatorial. All right, so it says number 4, label the beta hydrocarbons and circle any beta hydrogens. So we're going to label, we got to find our alpha. Alpha's here with the bromine. That's our alpha. It's a secondary. So we have 2 betas. That's a beta. And that carbon back there is a beta. Now it says circle your beta hydrogens. You have 1 beta hydrogen. Notice on the back you do not, because that's a CH3 back there. Okay, draw the other chair conformation. Well, we got to do a ring flip. Okay, so we're going to flip. That means this carbon goes up, and this carbon goes down. So then we go up, and then this carbon with bromine is down. And then we have to put in our substituent. So at the yellow carbon, we have bromine, and bromine is what? Axial up. So now we have bromine is equatorial up, because up stays up and axial becomes equatorial. Okay, we got to go to the back carbon here, and that's going up. There's your axial up, equatorial down. It doesn't matter, they're both methyls. And then this front carbon here, we've got, see how it's going up? So that's going to be the hydrogen, because what is this hydrogen here that we circled? That's equatorial up. So now it's axial up. And then the CH3 would be equatorial down. Here it's axial down. down stays down. Okay, so we did our ring flip, and this would be the more stable. Okay, in either conformation, are the Br and the beta hydrogen anti to each other? Okay, the answer is no. Okay, so for this to be anti, you always got to have the leaving group on the axial. So put your leaving group has to be axial. So either has to be up, or axial down. And then what you're looking for is the beta hydrogen has to be axial up or down depending on the bromine. Here we have it equatorial. Okay, so here this is called syn. It's on the same side. Okay, that's syn. Here it's on the same side. That's syn. So no elimination is going to occur. So would this elimination occur? No, elimination is not going to occur. It would be really hard to do. Okay, now we're on problem number 5. The structure in Model 2 has the bromine and the CH3 group trans. All right, what is that compound if you had to take that compound and draw a 3D structure? Okay, well, it's got CH3 here. It's got CH3 there. It's got bromine. Let's put that on the wedge. And then the CH3 is there. So that would be that compound. And you see how it's saying that these are trans. Okay, draw another structure where the bromine and the CH3 are cis. So let's just draw the bromine and the CH3 cis. Okay, so let's just draw that. Okay, and it says draw both chair conformations once your group has reached consensus to determine if either chair conformation is capable of undergoing the beta elimination reaction. All right, so I'm going to draw my chair, and I'm going to put the Br up. That's axial up, and then I'll put this CH3. This is equatorial up. So these have to both be up or both down. Okay, and then the ring flip. Now this is going to go up here, and this CH3 is going to go down. So I start here. Okay, so there's my CH3, and so that's where the bromine is. And now I need that to go equatorial up, hydrogen down, and then what's happened in the CH3? CH3 would go axial up, equatorial down. Now, I think if you were to put the CH3 here to block this, I'm just going to draw those like that. Okay, which one of these would work? You got to draw in your hydrogen here. This one would work. So you could take a base here, and it would take this hydrogen. Those electrons would push to the double bond, and the bromine would leave. Do you see how those are anti? 180. And then you could draw this. And it would look like that, the methyl, and then you would want to convert these to 2D. All right, so this would be that compound right there. Okay, so this would be capable of beta elimination because the Br leaving group and the hydrogen that's getting eliminated are anti to each other. Okay, so 6A, we are given two compounds, A and B, and this is what you need to be able to do on your additional problems and such on these rings. You need to label all beta hydrogens, determine which hydrogens will undergo elimination by redrawing the compound. You want to see if hydrogen and the leaving group can be anti, and then you draw your product if it can. If more than one product can be formed, predict the major isomer. And when I look at your additional problems, it looks like 8D, 7D, you're going to have to draw the chair conformation on D and also on B. So A and D, you'll have to do those. And then A and C, you've got to do Newman projections. We'll put a star on 7B and 7D because those are the ones that you're definitely going to see in your assessments for your open responses. And then 8, you have to decide whether something's SN1, SN2, E1, E2. So we'll look at that in just a second. Let's work 6. Okay, so I'm drawing the two-dimensional structure for 6A. Okay, we have to draw this in the chair. I'm just going to go ahead and put my VR axial because that's the one that has to happen. That puts the hydrogen there. Okay, so that's my alpha. And then my beta is here. But now beta I have to draw the way it is. So I got VR and CH3 are cis. So my CH3 has to be on the same side. That's up. And then this hydrogen is down. So this would be nice because it will work. So the base will come in here because the hydrogen is 180 anti. And there's my mechanism. And then I will draw my two-dimensional product where the CH3 is there. It's flat, no dashes and wedges at this point because those are sp2 carbons, alkenes. So that is that product. Okay. Now let's do B. Oh, did it want both of them? If more than one product, predict the major product. Yeah, so that's the more substituted. This is the other product that can form. Okay, so there's that hydrogen. But you also have this back hydrogen here. So the base can take this back hydrogen and the bromine leave. And then you basically have draw this a little better. I know I can draw that better. Okay, so that would be that. And what does that look like? This one. You see how this has two hydrogens and it gives you a di substituted, and this one has a tri substituted. So this is your major product. Okay, so B, it gives you the chair, puts Br in the anti, and then here you have CH3 here, hydrogen here, and then you have this one here. What does that product or that starting material look like? That would like be Br on the wedge and CH3 on the dash, so that's trans. The base cannot take a syn, so the base is going to take this hydrogen back here, and then you're going to get, here we can draw that chair out if you would like. I need to draw this longer. So there's that, and then CH3 looks like that, and that would be this product here. All right. Major product. Okay, so I need you to be able to do that. So look at 7. Number 8 is also in your additional problems here. And you have to just, oh, so this is trying to help you decide, is the reaction going to go SN1, SN2, E1, E2? So is it going to go SN1, SN2, E1, or E2, and you have to decide and you draw the major product. Okay? So the first thing I want you to do is the RX type. So you need to classify that. So you're going to do that, and then you know if it's primary and it's a weak, well, primary and strong. So if you have a strong nucleophile, that's going to be SN2. So primary and strong nucleophile. Okay. You also need to classify the solvent. So if you have to, acetone, there's acetone. DMF is this. You can look these structures up. I will go ahead and tell you DMF. This is polar aprotic. Acetone's polar aprotic. Okay, so these are really good for SN2 reactions and E2 reactions because you want your negative charges in these twos. Okay, DMF, we have that acetone. Water, you should know water's, those kind of solvents, these would be polar protic. So these are going to be great for solubilizing, stabilizing a carbocation. You're looking at SN1 or E1. So try to look at some of your notes and classify those and predict your major product. And I'd like to see the major organic products. If you give me all kinds of products, I'm looking for one or the other on this.